provides a very powerful computational infrastructure that's available everywhere that you can access it. Of course, cloud computing have many advantages compared with traditional data centers. Some of them are easy maintenance, cheap maintenance, and good scalability of the system. And of course, these advantages result in very rapid growth, popularity growth of cloud applications, cloud services, and cloud products. And these cloud providers, of course, need some tools, effective tools to calculate the performance measures of these systems, of their system, their infrastructure. If you consider a cloud system that has several cloud service providers, each of them having a number of virtual machines, when a request comes from the client, the dispatcher sends this request to one of the cloud service providers. But in case when user request requires very high amount of computational resources, it should be split up into several sub-requests so that it can be processed more faster. In this case, one of the most important performance measure in client's view is the response time of the system. The time passed from the request arrival of the cloud system until the request processing is finished, and the results are sent back to the user. Our aim in our work is to provide a tool to evaluate this mean response time of the cloud system. For this purpose, we consider a given model with K servers, each of them having a separate view. Customers arrive to the system in batches, which exactly 8 customers in a batch. Upon arrival, these customers are distributed between servers, so that each server receives exactly one customer. We assume that batch processes also integrate around them, and that service times of the servers are exponentially distributed. Then, in this case, the system behavior can be described in terms of by Mokrov process M, which consists of several components. Each component represents the number of customers on each server. The state space of this process can be described as in Formula 1. Then, for our further analysis, we need to denote some subspaces of states. XM that consists of spaces where exactly M customers are in the system. Then we need to calculate the station probability so that of the closed model. We introduce an extrographic order on the states of the space, and we assume that a state greater than other states if some of the components of the states are greater than some of the components of the second state, or but in case when these sums are we compare first components of vectors. If they are equal, we pass to second components of both vectors and compare them. And we continue this process until we face two different components in these vectors, and the vector states that is described by vector with component that is greater, and we consider greater than without. Then transition rate matrix can be derived, and in considering this lexicographic order, it has a form of three-diagonal structure, as it's shown. Blocks of matrix A can be described as by formulas 4, 5, and 6. You can note that diagonal blocks of this matrix have diagonal structure, and other blocks don't have any particular structure. And in terms of these three diagonal blocks, the diagonal matrix of transition rate, we can write equilibrium equations, system of equilibrium equations for this formal style. But this method, matrix methods, are not as fast as desired. Systems have a very large amount of servers and service providers. So these directly solving equilibrium equations may not give us a result for real numbers of servers in the cloud computing system. So we propose another algorithm to calculate station probabilities that can work for the real parameters of cloud computing systems. It's based on elimination method. We consider firstly we define time instance at which arrival of departure occurs. Then this time instance form an backward chain with the same space of states. Transition probabilities for this smart chain can be derived from the matrix A by the formula 8. Then we start the elimination method. We eliminate states one by one, starting from the largest number state, modifying the mark chain and modifying transition probability matrix by the formula 9. It is proved that such modification, even if it changes the values of the absolute values of station probabilities, they do not change the relations or ratios between station probabilities. So, we continue the elimination process until we have only 2 states left. And for these 2 states, we can write the equilibrium equation, global balance equations. And after that, passing by formula 10, we can calculate directly all the station probabilities. As I said, this method allows us to save the ratios between station probabilities, and starting with, for example, for P1, the station probabilities in the market chain, letting P1 be, for example, 1, we can calculate directly all other stationary probabilities, and then when normalizing them, we probabilities, we can calculate response time of the system. We assume that response time of each case of system be tau A, and mean response time of the subsystem can be calculated using this formula. And then the mean response time of the overall system can be calculated as the maximum response times for all subsystems. Next is the case study with 3 servers. The parameters are on the slide. We can create results of our analytical model with simulation results, and we see that their simulation results and analytical model nearly very close to each other, and compare it with the analytical result for infinite buffer capacity of each subsystem. As we see on the figure, we have with infinite capacity is growing because there is no losses, but simulation results for infinite capacity buffer for simulation and analysis results are very close. And to conclude, the proposal mathematical model for the computing system performance analysis interrupt an additional algorithm that can work on real parameters of our computing system. And numerical analysis shows that station probabilities calculated by analytical model are nearly the same as station probabilities calculated using simulations. Our further research will include non-constant batch size. For example, when a dispatcher decides that the request should be processed by only one service provider, or only 2, or any number of service providers, any number of virtual machines. And that's all. Next slide shows the references. And the presentation is over. Thanks for your attention.
Thank you very much. There's some questions.
Thank you so much for the presentation. A little basic question maybe. Why do you count on a mean time for the response? Because usually it's important to have some kind of SLA that time will not exceed something, and the mean time will be in this range. Because say if you have a patient in the hospital one with temperature 27 and now 45, mean time, mean is 36, but the situation is not good.
Of course, but the system behavior always, you cannot know how it will be, how many requests you receive. So it's one of the destination that allows to serve certain cost, quality of service for this system. Destination.
Why did you choose processes for description of system behavior?
Because macro process allows to receive some analytical results, analytical formulas, and of course many researchers say that it can
So your result is an efficient algorithm that solves stationary performance characteristics. And I was curious about how much the assumptions of your network setting influences on the applicability of the algorithm. Namely, say if you're in a more general setting where you have dynamic behavior of whatever, then Markov chain analysis tools that I'm aware of require quite complex algorithms.
Yes, we show that direct solving equilibrium equations give they're really slow. We use really slow, but the second algorithm we proposed based on the elimination method is much faster and it gives good results. It's also exact method, not the approximation, exact method, but it works very fast.
Yes, but I guess that your conjecture is then that this will generalize also to the parametric setting or the next setting that you are planning to work on. And is it something that you could, say the community, there's a community of people who work on taking Markov chain systems, the probabilistic systems. Is there something they could learn from these efficient algorithms, or vice versa? Is there something that we can use from the probabilistic algorithms?
There is a certain approach how to provide this algorithm and this elimination method. But in each case, it should be optimized for each system, for each market process. So the complexity is to the complexity of this method is to apply this elimination approach to a particular system.
Thanks. Yeah.